welcome this week to the weekly Space Hangout. I am your fill-in host again this week. I'm Dr. Nicole Gugliucci. I'm a postdoc with CosmoQuest, and I'm Noisy Astronomer Online. And I am filling in for Fraser Kane, who is still touring up and down the west coast of North America this week with his kids. So hi, Fraser. We'll try not to make too much of a mess. I am joined this week from left to right on my screen by Amy Shira Teitel. Hello. Amy is actually calling to us from Canada, so not her usual space, but yet she managed to bring a model rocket anyway.
Got my Saturn V, and I'll represent Canada in Fraser's absence. So.
God, I love you. We have Dr. Ian ONeill, who is rocking the fedora since I don't have mine with me today. So yay. Jason Major. Hello, Jason. And introducing Dr. Matthew Francis. He is a new participant, the guy with the bowler hat, new participant to the Weekly Space Hangout, and he is also running our Cosmo Academy, our online classes over at CosmoQuest. So we'll be sure to put in a plug for that in the show as well. But let's get right down to the newsy business. Oh, wait, quickly before we start with that, I want to remind you guys that you can comment or ask us questions on the YouTube page where this is broadcasting. On the Google event page, I'm having a little trouble getting that in Comment Tracker, but I'll be keeping an eye on that as well. That's also where I'll be posting links throughout the show. And if you are watching anywhere else on Google+, we are tracking those sources. And if you're using Twitter, you can use the hashtag #SpaceHangout, and we'll see that as well. So thank you all for joining us. Yeah, let's get started with some great interesting, controversial news about dark matter and whether or not it's been detected. So, Matthew, you want to start with that?
Sure. So, big news this week, press conference and big seminar at CERN, the European Nuclear Research Facility. It's one of those things. People were kind of toying with us a few months back, hinting that a detector, the alpha magnetic spectrometer on the International Space Station, was going to be announcing something really big in the month of March, and then it got pushed back to April, which is always, always the way it is, right? You push things back as long as you can when you don't have all your results yet. But the results came out this week, and big secretive thing. Everything was hiding from us. But the big hint was that there was something to do with dark matter in this experiment. And the results came out, and look at the paper, and what you see is interesting. Actually, it's a very interesting paper. What it shows is there's an elevated amount of positrons coming from somewhere, actually coming from all directions at once, which is interesting too. The positrons are the antimatter partner of electrons. And so having elevated numbers of those means that they have got to be coming from somewhere. And they could be coming from dark matter, but there isn't the telltale sign that that's really where they're coming from. You think, okay, let me see if I can do this. Okay, so if you had dark matter creating these positrons, you'd expect that with higher energies, you get more and more positrons, and then when you reach a certain point, the amount's just going to plummet like this. It's just going to go, boom. That's the technical language for it. But instead what we're seeing is it's very nice and smooth all the way out to the limit of the alpha magnetic spectrometer equipment. And so, in other words, it could be dark matter. It might not be dark matter, but there isn't enough in the data to tell us either way. So where are these positrons coming from? We don't know. But it's really premature to say this is dark matter or this isn't dark matter. So we'll have to stay tuned, in other words.
So it's a results, but they're not sure how to interpret it.
That's pretty much it, yeah.
What I'm hearing. Hang on, I'm going to share this plot. Maybe you can describe a little bit what's going on. in this
Is
plot.
just one thing. Isn't this a bit like the LHC results? We need more exposure time. We need more and more events to better see this structure if there is in fact a signature in these particle energies. So we just need more time. This is very preliminary, isn't it?
Well, I think the real question is whether is the higher energy. AMS is going to be able to push out to higher energies, and this is a very long-running experiment. It's been running for 22 months right now, and it's going to continue to run for the foreseeable future until the space station dies or the AMS dies. So they're going to be able to push out to higher energies, and there's nothing in the data that currently exists. So in other words, if it just refining the data that's already there won't show up dark matter. But if we push to higher energies, there might be that drop off instead of that gentle curve up.
So is this on the plot here? It's is it that stuff that's at the highest energy?
That's right. All the way at the right end of the graph.
This is the red dots. They've got really tiny error bars, which seems to be an important.
Yeah, it's beautiful. I mean, I think it'd be easy to say, oh, this is just crappy, but this is actually very beautiful data. I'm very pleased by the experiment actually, but so don't think I'm down on them.
We can quote Dr. Francis on this. This is not crappy.
Because obviously everybody defers to my judgment on this, but no, it's really nice looking data. It's just it's premature to say what it means yet.
Yeah.
Now, according to Dr. Ting during the press conference that they held, this is only what 10% of the data that's been collected already by the AMS. So they still have a lot of data to go through, or is that only 10% of the data that's going to be collected over the course of the experiment?
I think it's 10% that's going to be collected.
Okay.
I may be wrong on that, but I think it's only 10% of all the data they're going to get.
Okay, but still, there's going to be a lot of data to pull.
Right.
And so when that's accumulated, the answer will be there. I mean, or
one hopes, yeah.
One hopes. Okay, so this is. But which particular dark matter hypothesis is this? Would this be supporting? Is this the weakly interacting massive particle?
Yes, and this particular is a kind that's called self-annihilating dark matter, which sounds pretty wild. I was mentioning that positrons are the antimatter version of electrons. Mm-hmm. Well, in this particular model, these dark matter particles are their own antiparticles. So if you run two of them into each other, they annihilate, and one of the products of that is positrons.
Okay.
But of course, that's only one model of dark matter. So, and there's several different possibilities of self-annihilating dark matter. And again, I'm picking the brains of my dark matter experts who can tell me more about this. But if you want the fancy term for it, that's called neutralinos.
Yes. Okay.
But if this is true, then if you two neutralinos meet each other, they annihilate.
Mm-hmm. Gotcha. Okay, so no dark matter yet. Yet. So we'll keep an eye on that story as it continues. I want to take a brief pause to say we've got a comment from Michael on YouTube saying, "Happy First Contact Day, everybody." So all the Star Trek nerds out there, Zephyr and Cochrane made contact on this day.
What is First Contact Day?
Are you a Star Trek fan?
No.
Ah, okay. Well, we could fix that.
What does that mean?
It's when humanity first made contact with another species, in this case, the Vulcans. So.
Oh.
In the show.
Of course.
Yeah, it was of course. So, yay for that.
In other words, we're really late.
Yes, and we're dorks.
And they taught us about all that fancy warp drive stuff, which is cool and handy.
So, unfortunately, we have no warp drive stories today, but Ian, I think you had a little bit of Mars mission news to share with us.
Oh yeah, pretty cool. Yeah, that's fairly cool Martian news. Basically, the orbits of Earth and Mars are now in opposite ends of the sun. So basically the sun has now moved in the way of our communications with Mars. And it's basically called a Mars solar conjunction. And of course, this causes kind of issues when you want to try and communicate with Mars, because we're trying to fire our radio communications deep into the solar corona, which is the sun's atmosphere. And at the moment, if you could see Mars, don't look at the sun right now because it's so close to the sun. It's going to actually come very, very close to the limb of the sun, and basically, if we fired any radio transmissions through the atmosphere, it could interfere with the data, and any commands that we uploaded to like Curiosity or Opportunity or the orbiters, the Mars Reconnaissance Orbiter, Odyssey, or even the European Mars Express, it could cause problems. So basically, NASA announced yesterday that they sent the last command to Curiosity. So Curiosity is by itself now. Basically, it's not going to receive any commands until probably around about the 1st of May, when Mars actually moves away from the solar disk. Now, the sun isn't completely blocking our view of Mars. So basically, NASA's setting up Mars Odyssey, quite an old satellite now. It's a veteran in Mars orbit. It's been going since 2001, so it's another incredible mission. That's going to be continually relaying information. So it's basically going to be checking in on Curiosity and Opportunity, relaying information back to us. NASA knows that around about I think it's April 17th, when Mars makes its closest approach to the limb of the sun, that we're probably going to lose that data streaming from Odyssey, but it's still going to keep on trying to transmit to us. But basically, yeah, we're not going to be communicating with the Mars missions. I think NASA's going to pull back communications with Opportunity, the MRO, and Odyssey. I think it's on the 9th of April. Yeah, 9th of April until the end of April. But Curiosity is going to be alone for the longest time. They're not going to send any communications from yesterday until May 1st. So don't expect too much Mars news really for the next month.
Aww.
Kind of a shame, but
so
it's
really
a natural process.
It's just not doing anything for the next month because it can't receive commands, or is it actually taking observations?
Yeah, NASA, I believe, has sent commands for it to do limited science by itself. So it's doing its own thing for a while. But don't expect it to be drilling or anything complex like that. It's just going to be taking the rudimentary science. And also it's going to be uploading its data to the MRO. So the MRO, the orbiting Mars Reconnaissance Orbiter, is on record mode. So it's not going to be transmitting back to Earth during this period when Mars passes through this area of interference. It's actually going to be recording, and apparently it's going to end up recording about 40 gigabytes of its own science data, because it's continuously taking its own science data of the Martian atmosphere and the surface, and it's going to be recording Curiosity's data as well. So we got this little recording device around Mars, and it's going to download everything around about May 1st, when Mars is clear from the interference.
So then we'll get a big dump of data and all sorts of all sorts of discoveries from Mars on May 1st. That's excellent.
Yeah.
Well, I was going to ask, do you know if they did a big, did they get a whole whack of data before they're losing communications? Do they have something to do for the next 3 weeks?
I don't know.
Did they say anything? I have no idea. I'd ask.
I don't know. I mean, they've been preparing for this for a while. I mean, NASA sent out this press release back last month, and of course, these things are known to happen. They happen every 26 months between Earth and Mars. So I assume they had something set up. They actually had a manager for the conjunction. He actually organized this whole thing when they're going to be transmitting. So I assume they're probably aware of it. They probably downloaded more data, but I think the Curiosity team, they're probably going to be taking a bit of a break because they're not really going to have an awful lot of work to do. So it's like spring break on Mars, really.
I have a feeling there's always data to analyze somewhere.
There's always stuff to do.
They're not going to run out of stuff to do, yeah.
They're not like, screw you, I'm going home, staying in bed for the next 4 weeks. But they have been busy for the last, 8 months. So
right. Well, they can catch up on Walking Dead now.
Yeah, catch up on TV.
Sleep.
Sleep, whatever. Yeah. So elsewhere in the solar system, Jason, we have a new interesting molecular discovery on Europa.
Yeah, it seems that Europa, in addition to having a buttload of water ice wrapping around its surface, there's also hydrogen
Could you
peroxide.
phrase that differently?
No,
right, let's see.
nope.
No, I think
Nope,
that's
okay.
that's
Go
what
with
it's-
it. Just go with it.
So I'm going with it. There's also hydrogen peroxide on the surface of Europa. So that's pretty important in that if the hydrogen peroxide in the quantities that exist on the surface of Europa, if that can get down into the ice and go all the way down to the subsurface ocean, it could provide fuel, energy in the form of oxygen for microbes that are swimming around and scooting around down there. So, basically what we found is, for lack of a more advanced term, fish food on these all over the surface of Europa. Not saying that there's fish or not saying that there's food, but the stuff's there. So, it's pretty exciting. It's just one more thing that makes Europa really, really intriguing to go look for life and peer into it and drill down and melt a nice deep hole and take a peek at what's underneath. I believe that they found this. This was found. Let's see, Mike Brown from Caltech, and I'm not sure who. I can't remember who the other author of the paper was. But they used the Keck 2 telescope on Mauna Kea, and just basically looked at Europa, did some spectrography, and is it spectrography or spectroscopy?
Spectroscopy.
So they did some spectroscopy and basically got a better look at data that Galileo had started picking up on. They said, well, it was a little preliminary at that point. So what they're able to see with Keck 2 pointed at the hydrogen peroxide. And it seems to be mostly on the leading edge of Europa. So that's the side that's facing forward, basically Europa's windshield as it goes around Jupiter. And the peroxide is thought to be created by Jupiter's magnetic field. So it's processing stuff that's on the moon and making hydrogen peroxide. Very small quantities, but it's significant.
We just really want to see life on Europa.
Yeah, we all want to see. Yeah, we all want to see Europa squid and Europa fish and all sorts of awesome stuff swimming around down there and eating each other and everything. But this is step one.
There was some recent news about whether or not a Europa mission was going to get funded this week. Does anyone know about that? I just vaguely heard about that. Ian, you're nodding, so.
Yeah. Oh, can you hear me? Is it?
Yeah.
Yeah.
Weird. My computer's acting up. Yeah, there was news that came out, and it was Destination Europa. It's a group of scientists that are kind of loosely tied with SETI and also with other NASA institutions as well. And they announced, it was over the weekend, actually on Sunday, they said that the president had signed into law a component of funding for the rest of the fiscal year, which it goes up until is it September of this year. And basically it's a bill that's being signed for the use of cash to be used for science projects, and one of those projects kind of snuck in between, how to use rental cars to how to fund the James Webb Telescope, $8 billion of it. Sandwiched in between there was an allocation of $75 million to begin a Jupiter Europa mission. So this isn't $75 million is a drop in the ocean for any kind of mission, especially to Jupiter. But it is interesting in that only recently, back in December, it was NASA headquarters showed interest in a Europa Clipper mission. Now, a Europa Clipper mission is basically an optimization of funds versus science that can be got out of it. So it's not a Europa orbiter, which is a shame because that would be really, really cool. But the problem with a Europa orbiter is that it would need to be really heavy because it would need to have really hefty shielding on it to protect against Jupiter's radiation. So the predicted lifetime of such a mission would be just over 100 days, which would cost several billion for 100 days worth of science, which isn't really that great. Also, we're not at a point where we can say we're going to land a lander or or some sort of burrower onto the surface of Europa, because that's a bit premature, and that again that would cost tens of billions of dollars, even if it'd be possible with any kind of budget in the next 10 years with NASA. So really the most cost-effective mission that has been looked at is the Europa Clipper, which is basically a Jupiter orbiting satellite, and it's going to be making several passes of Europa, and each time it makes a pass, it will make scientific observations of the surface and whatever atmosphere it's got and its icy surface, and perhaps even search for any evidence for life, or the cycling that Jason was talking about, the cycling of the internal ocean with the surface. And it would be a really cool mission, and this is the first sign really to have 75 million signed into law that has to be allocated for a Europa mission by NASA. That is a very hopeful sign. Of course, there's no details yet, and this is only seed money for an investigation and preliminary prototypes or whatever. But it's good news. It's good news for advocates of any planetary science, and especially search for life. Because at the moment we're throwing all our eggs in one basket. At the moment, we've got all these missions around Mars, which is basically a dust bowl, and we're looking for any trace of life or past habitability. Whereas we got this cauldron of potentially organic stuff just sitting in Jupiter orbit. And of course, this isn't the only moon that's interesting. You've got Titan in orbit around Saturn. You've got all these other fascinating places we could go and see. So this is a very nice indicator that there may be a slight departure away from Mars science towards science in the outer parts of the solar system, but we don't really know. This is only a tiny amount of funding for a possible mission, so we don't really know yet.
Your Europa Clipper would estimated to be what, around $2.5 billion?
Yeah, they reckon that the limit was $2 billion. I think they're looking to have a mission for under $2 billion total. I mean, obviously there will be cost overruns or whatever, but $2 billion is really the cap, and that's what really got NASA HQ interested back in December. And it looks like it got some attention in the White House as well, so it's been signed into law.
Interesting. Yeah, I would recommend follow the Planetary Society for that.
Yeah.
This is where I originally heard from, so interesting.
Let's attempt a landing there.
We haven't been told not to yet.
No one said not to.
No one said not to. We could do it. We could do it. Okay.
So apart from the movie, a lot could go wrong.
Yeah, that's okay. We have a quick question from Josh Andrews asking if there's ever been any plans to, this is relating to the Mars story, if there have ever been any plans to send a relight satellite somewhere else on Earth's orbit, say a quarter of the way out, to avoid these conjunction communications problems. And I've never heard of such a thing.
I know the European Space Agency was looking at it. Sorry, is my mic on?
Yes, it is.
Okay. The European Space Agency had looked into it in the past, and I think it was just not feasible given that it's they were looking at putting it at one of the Lagrange points, so one of the points where it would not be interrupted and could sort of be a relay. But the articles I've read about it, because I did look into this a few months ago now, that it sort of wasn't worth it for like the 2 weeks every 2 years that you're missing in communications, because this would not be an insubstantial thing to launch and then to anchor it there with gravity. So I think it was just been like, it's possible, but nobody's really going to back it.
You know what they should do? You know what they should do? They should have some sort of a relay capability on the Sentinel program that B612 Foundation is planning on putting out there, because it's going to be at one of those Lagrange spots. So it's going to kind of be at that, that 90-degree position from Earth. Who knows? I mean, I'm just throwing it out there.
And also, really cool science can be done in those spots, because there's this theory that perhaps there's loads of Trojan asteroids just sitting out there. So wouldn't it be cool if we can actually send a mission out there to do some scouting around and also have a relay station? But also, there is a solar mission, the Stereo mission, which has got 2 satellites that are going around opposite sides of the sun. So for the first time in human history, we've got 360-degree capability of observation of the sun. So wouldn't it have been cool if we could add relay stations on those? So we've already got them out there, but
right.
All right, so there's cool
How
much
can you retrofit something that's that far away?
You can't right now.
Not now. Yeah. So.
Our robots are not good enough yet.
Amy, you have some interesting space history that ties into an event happening next week.
Yes, blast from the past, everyone. So next Friday, which means I'll be talking about this again next week, undoubtedly, is the anniversary of Yuri Gagarin's first orbital flight. So we all know Yuri Gagarin. He's kind of everywhere. Every year he pops up. He's the first cosmonaut and the first person in history to go around the Earth. So just
I got Vostok 2 on my T-shirt. See?
There you go. Nice. He was Vostok 1. So yeah, Soviets everywhere. Awesome. So we sort of tell the story of Yuri Gagarin blindsided the U.S. going into orbit before NASA got Al Shepard up on his suborbital flight, and we sort of don't talk about sort of the before and during and after bits. We just kind of talk about the fact that he did it. So I thought I'd talk a little bit today about how he ended up being chosen to be the first cosmonaut. Because how do you pick who's going to go first in a nation where image is everything? So when it first, the idea of sending a man into space first came up in actually about 1956. Sergei Korolev, who was sort of the unknown chief designer, or their answer to the American von Braun, we just kind of thought it would be neat. And 2 years later, he'd put 2 Sputniks up, and they're like, okay, let's get that guy. So they started recruiting. They went through the exact same process as NASA, actually, in terms of looking at like race car drivers, stunt divers, acrobats, midgets. Any kind of people before they settled on military test pilots, because they're the ones that could deal with G-forces and spot oncoming hypoxia and deal with all these kinds of things. And in 1958, all Soviet test pilots were basically the same age, had been through the exact same training, had flown the exact same airplanes. So in America, we had, I think, 110 that qualified for the first round, met all the basic requirements for the Mercury astronauts. The Soviet Union had over 3,000. They had this huge pool of equally qualified applicants, so then they had to pick one out of that many. So they did all the medical tests, the psychological tests, but then they also had this series of tests, and I have no idea how they tested this, but they wanted to see who had the right political allegiance and who could represent the communist way of life the best. And they looked into their backgrounds, not in terms of like, are you an unsavory Presbyterian or a very savory Presbyterian. It was, where did your family come from, and have you ever said anything against the system? And as sort of the group got whittled down and down and down, there were 20 that made it into the first training group, and they were cosmonaut candidates until they were candidates until they flew. So all these candidates are going, and when it comes down to the wire, they've got the Vostok built. They're about a year away. They choose 6 to be sort of like the prime candidates, and the 6 were chosen because they were the shortest, because the Vostok spacecraft was not very big. So height plays into it right at the end. And Yuri Gagarin wasn't actually the standout of his class in terms of his intelligence, his background, his intellect, but he was a farmer's son. And he grew up in a communal farming rural area. He was an all-around nice guy, and he sort of went against his family tradition of carpentry to pursue the Soviet Air Force system. So he rose up through the ranks of communism to become potentially their greatest asset. And no one thought he was that great, but Sergei Khrushchev, the Soviet premier, thought he was just tops, and he wanted this good-looking young man who could prove that the Soviet way of life could bring you to greatness. And that's why Yuri Gagarin ended up in the first flight, because he fit the profile more than he fit what you needed to be a cosmonaut. They couldn't do anything on Vostok 1. He didn't even have the self-destruct code. He was really just kind of crammed in there. But yeah, he was a really good face for the Soviet space program. Which is a really weird thing to think about. Your first person in history is chosen because it's got a good face.
So
good
how tall
history,
was
good
your
pedigree? You know what? I don't know off the top of my head, and I was actually looking into this yesterday. If anyone has Google that won't crash when they use it, look it up and let me know. Yeah.
Cool. Really cool. And so
Fun
now
facts of the Soviet space program.
Yeah. And so next Friday is Yuri's Night, which is a big worldwide party for human spaceflight. And so we just had a hangout about this on Wednesday, so you can see that on our CosmoQuest page. We talked with one of the organizers of Yuri's Night. So regardless of nationality, the idea of Yuri's Night is now to bring together humanity to celebrate and have a big party. Not just, not necessarily to do, education and metrics and all that, but to have a party celebrating human spaceflight in honor of Yuri Gagarin. So that's pretty cool.
Yuri was 5'2".
What? Really?
Yuri was 5'2".
Was really short.
Really?
Taller than Yuri Gagarin. So yes.
That's like me and Amy.
That's really because that's really interesting because the Mercury astronauts had to be between, I think it was 5'7".
Yeah, 5'7". I think Gus Grissom was 5'7".
Because he was like 5'6.5" or something. He like just squeaked under. He was the short one. That's really little. So yeah, all the first guys that flew were the short ones.
Yeah.
Woohoo! Geraint Titov, who flew in Vostok 2, your shirt, Jason, who's also must have been somewhere around that height. Because
They didn't have adjustable tilt steering in those days, so you had.
I don't think they had adjustable anything. It was like you cram in now.
Yeah.
You fit in this little metal can, and that's how it works. Yeah. But still, awesome achievement, and go Yuri.
Yeah.
So
wicked what they pulled off.
However you got up there, go Yuri. We have a slew of astrophysical news to talk about as well. Let's start with Kepler looking at a white dwarf and warping what we see because of gravity.
Yeah, it was kind of cool, this news that came out. I think it was yesterday. And basically a bunch of Caltech astronomers used some Kepler data. And so Kepler data, after a certain period of time, is publicly available. So these astronomers got hold of this Kepler data and started surveying their own stars. And they, one star, I can't pull up the name of it because whenever the Google Hangout runs, everything else stops, apparently. They focused on one star, and they thought they saw a transit of a massive planet. Now, Kepler looks for exoplanets by looking for their silhouette as they pass in front of a star. So there's a slight dimming of starlight in the Kepler field of view, and then Kepler knows that a planet has passed in front of that star. And these
KOI 256, Ian.
Was it?
KOI 256.
Oh, I know it well. Yeah, and KOI means Kepler Object of Interest.
Oh.
Which is kind of cool. So they thought they saw a massive planet, like a Jupiter gas giant, pass in front of the star. But there was something weird. They did some follow-up observations with the Palomar Observatory down here in Southern California. And there's another method of looking for exoplanets, not just looking for them to passing in front of the star. Also, you can use the radial velocity method. So basically, you look at the spectroscopic, the spectrum of starlight from the star, and you can see it slightly shift as the star wobbles because of the gravity of the planet going around the star. So every planet in our solar system all have their own little tug on the sun. So if you're an alien observer, you'll see our sun slightly move around as these planets orbit around the star. So these astronomers, they thought, okay, we need to do follow-up observations. We've got the Kepler data. We're going to get the Palomar observations as well. But they discovered something really weird. This star didn't have something orbiting it. It was orbiting something, which is kind of shocking. You've got a star. You expect planets to be orbiting it. It's not going to be wobbling too much. But this one was actually wobbling like a spinning top. So then they went back to the drawing board, and they wondered what the hell is going on. Anyway, after a long bit of detective work, what they actually found out was this is actually a red dwarf star was in orbit around a compact binary partner, a white dwarf. So this white dwarf is actually about the size of the Earth, but it packs the same amount of mass as our sun. So this poor old red dwarf is actually in orbit around this tiny, tiny white dwarf. And what was happening, they were noticing a dip in starlight as the white dwarf went behind the red dwarf. But when the white dwarf went in front, bear in mind, the white dwarf has got an intense gravitational field because it's very, very small and compact. whenever the white dwarf passed in front of the red dwarf, it would slightly enhance the starlight of the red dwarf. This is called gravitational microlensing, and it's been used before to discover far-flung planets that pass in front of distant stars. And basically what happens, the gravity of these massive planets or other stellar bodies like brown dwarfs, when they pass in front of distant stars, they can focus the light through the gravitational warping of space. So it acts like a natural lens. So it's like it's almost like a magnifying glass, amplifying that light. And what has happened in this binary pair is that the white dwarf passes in front, its intense gravitational field enhances the light from the red dwarf, creating only a very, very slight increase in brightness. So rather than a decrease in brightness, I actually saw an increase in brightness as the white dwarf passed in front. And it's the first time microlensing has been done on a binary pair, and it's kind of cool. And only Kepler could have done it, because Kepler's got a very, very sensitive eye to these slight dips in light. So not only is it detecting transits of planets, it's also detecting eclipsing binaries, which is kind of fascinating.
Yeah, I've got this is of course an artist conception of what it would look like, but you get an idea of what the smeg is going on.
Yeah, so the light is, as shown in that diagram, is you can see the light, the orange of the red dwarf actually being bent around the white dwarf's gravitational field. So it's Einstein's general relativity meeting Kepler's laws of motion, which is kind of fascinating.
Yay! Yay! I love fun astronomical mysteries.
Ian, is there any thought that these two stars are sharing material, or would they not be able to detect that with Kepler?
I don't know. They followed up with the GALEX, I think, GALEX Observatory, which analyzes light, ultraviolet light from the stars in Kepler's field of view, and they didn't mention anything about the sharing of material. I'm sure they'd be able to detect it, but that's how they managed to. It wasn't just Kepler; it was also the Palomar ground-based observatory, other space-based observatories, all zoned in on this one star, and they collected all the data together to arrive at the conclusion that they're actually seeing this warping of space-time. And so I'm pretty sure that if there is any sharing material, they would be able to detect it, but they didn't mention it in the press release.
It's probably unlikely, because usually when you have sharing material, that's when a star is close to the end of its life and it blows up really, really huge. Like when our sun gets close to the end of its life, it'll be about the size of Earth's orbit. And so red dwarf does not reach that point in its life. So it seems, again, not reading the article, it seems very unlikely.
Yeah, and we don't know the orbital distance either, because I don't think they were tight. They're not extremely compact. I think they are. There is quite a distance between them, so the sharing of material will be minimal, if anything.
Cool. Well, speaking of white dwarfs, we have a story about a very distant supernova, which is tied to what happens when white dwarfs go bad. So, Jason, do you want to pick this one up?
Sure thing. And
Okay.
Dr. Francis, if you have anything to add to this, feel free to jump in and add or correct any of my glaring errors on this one. Basically, astronomers using the Hubble Space Telescope over the course of a 3-year survey have found what appears to be the most distant Type 1a supernova ever found. And the light from this supernova has arrived on Earth after 10 billion years. So, they're looking, it's hard to say, distance and back in time, 10 billion years to see the light from a Type 1a supernova. Type 1a supernovae are important because they're used to gauge distance across the universe. It's a tricky thing to figure out exactly how far things are. So astronomers use the Type 1a supernovae as standard candles because they know how bright they're going to be. I believe the measurement is let's see, when that supernova erupts, or a Type 1a supernova erupts, the brilliance is equal to 5 billion suns, and it's pretty consistent like that. So if they see one from one distance, and then they see another one, and that one's dimmer, then they know that the dimmer one is coming from much further away, and then they can measure how far away that thing is. So, but this one that they've spotted is the furthest Type 1a yet, and that's 10 billion light years distant. And it also helps to figure out exactly what type of stars make Type 1a supernovae. There's been two ideas on the table. One is that there is a white... Let me step backwards. It's understood that these type of supernovae are the result of binary stars, kind of like what Ian was just talking about. One of those stars is expected to be a white dwarf. Whether or not the other star is a white dwarf as well, and they're co-orbiting and eventually merge and go a supernova, or whether the other star is, and Dr. Francis, maybe you can help me out on this, it's a red giant. Yes, correct. The other star, and the other scenario would be a red giant that's having its material.
It's something that's spilled over into the gravitational influence of a white dwarf. Yeah.
Yeah.
It's basically they're sharing the same. The gas from the other star has basically expanded to engulf the white dwarf.
Mm-hmm. So that's the other scenario. But these findings of this 10 billion light-year distant supernova kind of point to the idea that they're caused by two co-orbiting white dwarfs as part of a binary pair. The reason being is because there's been a sharp drop-off in the supernovas that have been spotted between 7.5 and 10 billion years ago. I'm going to say 10 billion years ago. So what that means is there's been less time for the white dwarfs to form. There's much less of a scenario that you're going to have a binary pair made up of two white dwarfs, as opposed to having a little bit more time because, in the other scenario, one's a white dwarf and one's a red giant. Now you're looking at me like I'm getting this wrong, and I very well might be. So clarify that.
I'm rolling through it in my head now, so I looked over it quickly. But yeah, it takes a long time to create a white dwarf because it comes from a middle mass or middle mass star, kind of like the sun. It's a sun-like
star.
Right. So the sun takes 10 billion years to turn into one. So for this to happen within the first 3 billion years is a special case, I think, to forming white dwarfs so quickly.
Right. So then to have two of them as part of a binary pair takes a certain amount of time. So what they found is, there's been a drop off in how many of these supernovae are spotted going back that far in the universe. So this furthest one, at 10 billion years, I think the one before that was about 9 billion years. So you've got the spacing that's happening here. So it kind of points to the idea that these supernovae, these standard candles of measurement through the universe, are probably more like a white dwarf binary pair than they are the other having a red giant and a white dwarf. So that helps them know exactly what makes these Type 1a supernovae, and it also kind of says, where a lot of the elements in the universe, the early universe, would have come from. Because when these stars go supernova, they throw out a lot of heavy metals and heavier elements, things that are used to build stuff like planets and other stars and people and frogs and great white sharks and stuff. So to know where these elements come from, yeah, I mean without Type 1a supernovae, we wouldn't know how far things were, and we wouldn't have awesome great white sharks.
Chomp, chomp.
Yeah, exactly.
Sorry, that's my yeah. I'm still stuck on the idea of why it would take longer to form a white dwarf red giant pair.
No, it would take. Okay, I believe it would take longer to have the two white dwarf pairs. Correct.
That's what I would think. But then why? Oh, you're shaking your head no, but we can't hear you, Matthew. Oh yeah.
I didn't say anything yet. I just shook my head. No, it takes less time to create a pair of white dwarfs because, let's see, now I gotta get the reasoning in my head. It's because of the time not just to make the white dwarf, but to make the system evolve. So basically, to have a close orbiting pair of white dwarfs, what you have is a system that basically was always evolving together from the very beginning. So the estimate that's sticking in my mind is that it takes about 400 million years to make make a pair of white dwarfs in this type of system for this particular kind of supernova
But
ancestor system.
isn't it just that the birth masses of the two stars, if whether they're similar or really different, like why would that? I guess I'm wondering why that would matter, unless it's the fact that the second star takes so much longer to get there, and that's why.
I believe
Is that what I'm
that's
missing?
it, but
Okay.
I maybe we should pick the brains of a white dwarf expert next week.
Awesome. Okay. So you are seeing us figure this out in real time, people. So sorry. Okay, so we have one more story to go involving black holes eating stuff. So, Ian, do you want to start that, or Matthew? I know you guys both worked on that this week. Okay.
Why don't I start it?
Okay.
And then Ian can jump on me if
Yes.
there's anything I miss or say wrong. Okay,
That's
so
right. You can take it.
all right, so this is preface this a moment to set up the idea. As probably many of you know, at the center of pretty much every galaxy we know, there is a supermassive black hole that can be millions or even billions of times the mass of our sun. And there's also, as we're just beginning to learn, there's a lot of planet-sized objects roaming around galaxies that aren't attached to any planet. These are, sometimes they're called rogue planets or something like that. But the main thing is that these can be planet-like objects. They can be like Jupiter. And so there's a lot of these things around. And so looking through data that's been collected from monitoring the sky and gamma ray light, astronomers picked up a flare of gamma rays that fluctuated a lot. Now, when stuff falls onto a black hole, it creates this accretion disk and maybe jets of matter, and this stuff produces a lot of light. But that tends to fluctuate slowly. The amount of light we see doesn't change a lot over short time spans, whereas this particular incident in this galaxy that's now I've got to remember how far away it is. It's not that far away in cosmic terms, I think.
Yeah, like 46 million light years away or something.
Yeah, I was going to say it's only. Well, it's pretty close by cosmic terms. Yeah, but the main thing is that you don't expect things to fluctuate over a period of weeks, which is what they were seeing from this particular black hole. And not only that, it started fading when they started monitoring it. So basically you had this burst, it peaked, and I'm doing a lot of plot hand motions here, interpretive dance of plot, but it faded over time. And so what that meant was this was kind of a one-time event. You had a clump of matter falling onto the black hole in a fairly short time span. And so by working backward, they figured out that the amount of mass responsible would have been about 10% of, it's actually about the same mass that Jupiter has. So that seems like a lot of mass, but of course in cosmic terms, again, it's not that much. But even that little amount of mass could produce a fairly substantial burst of gamma rays. And so by working backwards and by comparing this to theoretical models, computer simulations, the astronomers figured out that it was probably one of these rogue planets got too close to the black hole. And what happens when something gets in strong gravity, you have, I talk with my hands a lot. When you have something get close, the gravitational pull on the near side is going to be noticeably stronger than the stuff on the far side. Well, a planet as big as that, something that's about 14 times the mass of Jupiter, is going to be made of gas. It's going to be mostly hydrogen. And so what that means is that can be deformed a lot. That can be squeezed and squished. And so basically what happened is the force on the near side versus the force on the far side ripped off a chunk, about 10% of the mass of this planet. Just ripped it off and it landed on the black hole. So you end up with a slightly smaller planet, slightly fatter black hole, and this burst of gamma rays coming out. And so think about this black hole as being, having a bit of a snack off of this rogue planet that happened to get too close, and let that be a lesson to all of us.
It was kind of funny, actually, because what you said just then, how a black hole waking up and having a snack, I got in serious trouble with some of our readers for even mentioning that it woke up or had dinner or a planet was on the menu. It was like, guys, this is science communication.
Get the munchies.
Get the money. Yeah, that was my original title. I did that before.
That's what the URL still says.
Yeah, the URL does, because that was my original title. But then I realized I already used that because there is actually a gas cloud heading towards the black hole at the center of our galaxy, and they think that this gas cloud is actually going to start being ingested by Sagittarius A star. The supermassive black hole in the center of the Milky Way. It's going to start.
Stay tuned for September. I think that's.
It's coming up. So we got another big year of cool stuff going on. So keep an eye on our black hole. We're a safe distance, though. We're okay.
Yeah.
But can I say just interrupt this communication? Matt, you've got a fantastic background there. You've decided to fill up your wardrobe with science books. I love it. Because if you look at mine, it's full of my wife's clothes.
What? Tangential.
Yeah. I was just completely in awe of your books. I was thinking, where is his books? Oh, it's in his wardrobe.
Let's go look at his books. I can't read the titles, but that's in your closet. I saw numerical recipes. Yep, numerical recipes in C.
So that's one that's familiar to many of us who
love it.
Graduate school.
The moral of the story is don't pick on Ian for his titles because they're funny.
Well, actually, I'll see your title and raise mine. I used the phrase "om nom nom" in my title, and that is the first time Ars Technica has ever published the phrase "om nom nom" in anything.
Love it.
So, in the context of a black hole eating a planet.
See, I have Ian as my editor, so I get away with fun stuff, which I love.
You get clearance.
Yes. We have a related question from Polygona9 on YouTube asking if black holes are necessary for our universe to work. And I don't know what you mean by to work, but black holes are definitely the, interestingly, black holes are the least weird and most sensible explanation for a lot of these things that we see.
Yeah, I think, Nicole, you wrote an article on this, didn't you, about the central black holes can turn on and off star creation in galaxies.
Oh,
so,
yeah,
yes.
yeah. They're an important part of the evolution of galaxies and the end products of stellar evolution. But they are even though they sound like a weird object, they are the least weird thing that fits all the data that we have.
One question I tend to get from a lot of people when I talk about black holes is they're kind of confused as to how a black hole, which supposedly is has so much of a gravity that light can't escape and all that other stuff, is flinging out material. They're like, well, if stuff goes into a black hole and can't come out, then how come we can see anything from it? So then I have to explain how they're messy eaters and all that other stuff, and things get spit out and magnetic fields, and usually by that point their eyes glaze over because they don't really want a whole answer. They just
basically
wanted to
yeah, basically it's a communication error on our part. I take the responsibility as a scientist and science communicator.
I blame Nicole.
Blame me.
Yeah, I blame Nicole. I should have just blamed you. I should have just said just defer all complaints to Nicole. She's the professional.
I can take it. It's all good. But we say it's the way we say everything goes into a black hole, but it's everything that gets too close. It's the stuff that's just outside that too close that can get energetic and spewed forth. So that I think is the difference where we confuse people in the way we communicate it. So black hole's cool. We can still see what they do to the stuff around them. That's I think the important part. So, all right, that is all we had on tap for this week's Space Stories. I want to thank you all for coming along. Before we do our sign-off, I want to ask Matthew to do a brief plug for the CosmoQuest classes that we have coming up.
Yes, indeed. I am I didn't put it in my tag, but I am the director of Cosmo Academy, a new position. I am the first, I guess. But we're offering 2 classes starting this month. The first is a class on stars and stellar evolution, which means basically starting from the cloud that makes stars and going all the way through to the death of stars, and talk about where we came from in the context of actually what Jason mentioned earlier. We come from stars. The atoms, pretty much every atom in your body came through a star at some point. So that class will cover that, and that begins in not next week, but the following week on Monday.
April 15th.
April 15th, thank you. The date just blanked out on me. And then the following week, on April 23rd, I will be teaching a class on cosmology, the study of the universe, its history, contents, and all this stuff about dark matter. Well, that's going to be a lot of the class. So if you wanted to know about dark matter, dark energy, a little bit on black holes, that's a great opportunity for you.
Yeah, so check that out. I put the link to that. It's cosmoquest.org/classes. There are links to the Eventbrite pages where you can sign up for the class. It's done Hangout style like this, but it's in a private Hangout. The class is limited to 8 people. You get taught by either Dr. Matthew Francis here for cosmology, or Ray Sanders, who taught our first 2 classes for the Sun and Stellar Evolution class. And Pamela Gay and I will occasionally pop in and say hi and check out the final projects and pop in when there's a topic of interest for us and join the conversation. So check that out. That's cosmoquest.org/classes. You can continue your lifelong learning. Let's have everybody tell us where we can find you, starting with Amy.
Hello. Okay, just checking that my mic is back on. So there's a bus going by my window. I am at
Canadian bus.
Canadian bus, Toronto Transit Commission bus. If you Google Vintage Space, I come up. Otherwise, my website is amyshirateitel.com, just my full name. I'm also at Discovery News, Device, Motherboard, Scientific American, and others.
She's the hardest working freelance
Google
writer. She's the hardest working freelance writer in space, or on Earth about space. So, Dr. Ian ONeill, where can we find you?
Yeah, I'm the space producer over at Discovery News, so you can find me there, discoverynews.com. We've got more than just space. We've got history, Earth, anything technology-wise, so check us out. Also, you can find me on Twitter, where I spend most of my existence, AstroEngine. So tune in there. I've got a blog as well, astroengine.com, but I very rarely update it, so I need to do that. But that's me.
Okay, and Jason Major.
My mothership is called lightsinthedark.com. I'm also a space blogger on Discovery News, on Universe Today, and you can find me on Twitter at JPMajor.
Awesome. And Dr. Matthew Francis.
Well, I have a number of websites. The flagship site is bowlerhatscience.org. Thanks to my trademark bowler hat. I also blog at galileospendulum.org. That's the specific science blog. And then I write for Ars Technica, XX Science, BBC Future, and available to write for other sources as well.
Sweet. And I'm Dr. Nicole Gugliucci. I live over at CosmoQuest and noisyastronomer.com. The next Hangout will be the virtual star party on Sunday evening. I don't know if this is the one where Fraser and Scott Lewis are actually going to be in the same place at the same time on Earth, but that'll be a treat if they're doing that. So check out the virtual star party on Sunday night, and we'll be back with the weekly Space Hangout next Friday, same time, same place on the interwebs. So thank you everyone for joining us. Bye. Important.
Yeah, it's beautiful. I mean, I think it'd be easy to say, oh, this is just crappy, but this is actually very beautiful data. I'm very pleased by the experiment actually, but so don't think I'm down on it.
We can quote Dr. Francis on this. This is not crappy. Not crappy.
because obviously everybody defers to my judgment on this. But no, it's really nice looking data. It's just, it's premature to say what it means yet.
Yeah, yeah.
Now, according to Dr. Ting during the press conference that they held, this is only what 10% of the data
Right.
that's been collected already by the AMS. So they still have a lot of data to go through, or is that only 10% of the data that's going to be collected over the course of the experiment?
I think it's 10% that's going to be collected.
That's going, okay.
I may be wrong on that, but I think it's only 10% of all the data they're going to get.
Okay, but still, there's going to be a lot of data to pull.
Right.
And so when that's accumulated, the answer will be there. I mean, or an answer.
One hopes, yeah.
One hopes. Okay, so but which particular dark matter hypothesis would this be supporting? Is this the weakly interacting massive particle?
Yes, and this particular is a kind that's called.
So it's A results, but they're not sure how to interpret it.
That's pretty much it, yeah.
What I'm hearing. Hang on, I'm going to share this plot. Maybe you can describe a little bit what's going on in this plot.
Just one thing. Isn't this a bit like the LHC results? We need more exposure time. We need more and more events to better see this structure if there is in fact a signature in these particle energies. So we just need more time. This is very preliminary, isn't it?
Well, I think the real question is whether is the higher energy. AMS is going to be able to push out to higher energies, and this is a very long-running experiment. It's been running for 22 months right now, and it's going to continue to run for the foreseeable future until the space station dies or the AMS dies. So they're going to be able to push out to higher energies, and there's nothing in the data that currently exists. So in other words, if it just refining the data that's already there won't show up dark matter. But if we push to higher energies, there might be that drop off instead of that gentle curve up.
So is this on the plot here? It's is it that stuff that's at the highest energy?
That's right. All the way at the right end of the graph.
This is the red dots. They've got really tiny error bars, which seems to be also where I'll be posting links throughout the show. And if you are watching anywhere else on Google+, we are tracking those sources. And if you're using Twitter, you can use the hashtag #SpaceHangout, and we'll see that as well. So thank you all for joining us. Yeah, let's get started with some great, interesting, controversial news about dark matter and whether or not it's been detected. So Matthew, you want to start with that?
Sure. So big news this week, press conference and big seminar at CERN, the European Nuclear Research Facility. It's one of those things. People were kind of toying with us a few months back, hinting that a detector, the alpha magnetic spectrometer on the International Space Station, was going to be announcing something really big in the month of March, and then it got pushed back to April, which is always the way it is, right? You push things back as long as you can when you don't have all your results yet. But the results came out this week, and big secretive thing. Everything was hiding from us. But the big hint was that there was something to do with dark matter in this experiment. And the results came out, and look at the paper, and what you see is interesting. Actually, it's a very interesting paper. What it shows is there's an elevated amount of positrons coming from somewhere, actually coming from all directions at once, which is interesting too. The positrons are the antimatter partner of electrons. And so having elevated numbers of those means that they have got to be coming from somewhere. And they could be coming from dark matter, but there isn't the telltale sign that that's really where they're coming from. You think, okay, let me see if I can do this. Okay, so if you had dark matter creating these positrons, you'd expect that with higher energies, you get more and more positrons, and then when you reach a certain point, the amount's just going to plummet like this. It's just going to go boop. That's the technical language for it. But instead what we're seeing is it's very nice and smooth all the way out to the limit of the alpha magnetic spectrometer equipment. And so in other words, it could be dark matter. It might not be dark matter, but there isn't enough in the data to tell us either way. So where are these positrons coming from? We don't know. But it's really premature to say this is dark matter or this isn't dark matter. So we'll have to stay tuned, in other words.
So welcome this week to the Weekly Space Hangout. I am your fill-in host again this week. I'm Dr. Nicole Gugliucci. I'm a postdoc with CosmoQuest, and I'm Noisy Astronomer Online. And I am filling in for Fraser Kane, who is still touring up and down the west coast of North America this week with his kids. So hi, Fraser. We'll try not to make too much of a mess. I am joined this week from left to right on my screen by Amy Shira Teitel. Hello. Amy is actually calling to us from Canada, so not her usual space, but yet she managed to bring a model rocket anyway.
Got my Saturn V, and I'll represent Canada in Fraser's absence. So.
God, I love you. We have Dr. ONeill, who is rocking the fedora since I don't have mine with me today. So yay. Jason Major. Hello, Jason. And introducing Dr. Matthew Francis. He is a new participant, the guy with the bowler hat, new participant to the Weekly Space Hangout, and he is also running our Cosmo Academy, our online classes over at CosmoQuest. So we'll be sure to put in a plug for that in the show as well. But let's get right down to the newsy business. Oh, wait, quickly before we start with that, I want to remind you guys that you can comment or ask us questions on the YouTube page where this is broadcasting. On the Google event page, I'm having a little trouble getting that in Comment Tracker, but I'll be keeping an eye on that as well. That's